But let's start now with
the first group of sensor fusion techniques.
State estimation techniques. So, as we said, these techniques aim to determine the state of a given system, which can be obtained from the analytical or empirical model of the sensor. We will see this, what this means later. These techniques include a large variety of
techniques and algorithms, like
maximum likelihood and maximum posterior estimation, which is quite familiar. I think it's familiar to most of you guys, and linear Kalman filter. So let's try now to explain the first one of the sensor fusion algorithm of our lecture, the maximum likelihood and the maximum a posterior estimator. Let's try recap our example before. We are trying to estimate the constant of gravity, the G. So our state now is G. What we have two accelerometers or two sensing units that can give us two observations, Z1 and Z2, and we have a noise description. So we know that our accelerometer are not perfect, and actually our observation that we do, or our measurement, are affected by a random variable V1 and V2 respectively, which can be described as a random Gaussian noise. So the ML estimator gives us a technique to estimate the value of G of X, which is G in this case, maximizing what we call the likelihood, so the probability of the observation Z1 and Z2 given the value of X. The maximum a posteriori criterion instead can be used only if we know the distribution of our state X. So by maximizing what we call the posteriori probability, so the probability of the state given the observation. Here, right part of the slide, I summarize the procedure to get a maximum likelihood estimation. So on the first step, we write the likelihood, so the probability of the observation given the state, which is on the assumption of the two random Gaussian noise of the accelerometer, is described by this formula here. So as we can see, we calculate here the log likelihood, and we obtain a expression of the log likelihood, which is then can be shown, is it optimized by this value of the G. So given our Z1 and Z2 observation, the best value of the constant of gravity is obtained by this formula. And this is what we call the maximum likelihood estimator of the two observation. So since in this case we have a really simple case, G is a deterministic parameter which is constant in time. I mean, this is just an assumption, but it's quite true. The maximum likelihood estimator is the same of the maximum a posteriori. Of course, this is not valid if, for example, our state G is a random variable as well. For example, think about the estimation of the magnetic field in a specific area with two magnetometers. In this case, we can model our magnetic field as a random variable, and so the maximum likelihood and the maximum a posteriori estimator are not the same. In this case, I don't want to give any detail about these two estimator, but what I want to show here is how we can use some techniques that we frequently use in many domains as a sensor fusion algorithm.